Now, you said, well, it could have been a -4, -4, -1. That means one's going in what? One direction, going through the paraboloid, and the other one's coming out of the paraboloid. You got it. I mean, you can actually draw them on that picture if you want to. Like, one's going like this, one's going like that. Right? +1 for z means it's got a slight what? Increase of 1 there. Or decrease of 1 unit. There you go. Okay, let's try another one of these. Can you find the equation of the tangent plane to this surface? Hold up. This way you're like, okay, Professor Master, you've been giving us too many problems where the partial derivatives aren't so hard. So I gotta use ones with e's. Eventually I'll keep working on ones with natural logs and stuff like that so we can practice with it. Alright, z equals e to the 4x plus y squared. The point? How about y is 2, but this time x is -1. I don't know what to use for z though. This out of the way. This out of the way. Get this out of the way. That's the equation.
So you have to put those points, right? Plug them in.
Yeah.
So that
Anybody know what that z value would have to
e
be?
to the power -4.
What's e to the 0? 1? Good. And you saw I just made this up, so this would have to be a 1. I'm glad. I want you all to look at that and figure it out because the problems we're about to do after it's in section 14.4. Sometimes they don't give you that z value. So I want you to go, how can I get it? All you gotta do is plug them into the original function, right? Very good. Very good. If they don't give you that z naught, you're like, I can go figure it out. All right, let's work this out. It's pretty easy. Z minus 1. X plus a 1, right? Y minus 2. What's Fy? And what's Fx? And then we'll plug in the points. So what's the derivative with respect to x? Partial derivative. I used to say partial derivative. The partial with respect to x. 4 times e to all this junk. Nice. 4 e to the 4x plus y squared. Sometimes this throws people off to like, what are you doing? So you gotta think like, how did someone differentiate y equals what? E to the 5x plus 2, and you're like, 5 e to the 5x plus 2. You gotta think everything else is constants. And then would you plug in the points? What number do you get? So you evaluate this at the point, -1, 2, 1. And 4 times e to the 4x squared, 4x plus y squared becomes 4 times e to a 0, which is 4. Now this has a different partial derivative. What's the partial with respect to y?
2y.
2y e to the 4x plus y squared. So 2 times 2 times. Oh gosh, is it the same number?
Yeah.
Gosh, I don't want you to think these are always the same that happen twice in a row. Sorry about that. And these, sometimes you get 0s and 8s and -1s and -3s. It can be fractions, but this turns out to be 2 times 2 times e to the 0. Right? And you plug in that point, and you get 4 root m. Tangent plane? Is that okay with that? Cool. And I love it. You all okay with that partial derivative? Nice. Okay, sometimes the most bizarre partial derivatives can sometimes be something like that. No, everyone, we won't find the equation of the tangent plane of that surface. But I was just curious. Does anybody know what fx would be? Because you gotta think of it like e to the 5x, where the y is the constant. So you get y times. There you go. Isn't that weird? But she's right. That is correct. Very good. And Fy would be similar. What would Fy be? X times e to the xy. So just keep that other thing held constant. Treat the other variable like a 2. Nice. Hey, doing a great job at this. Now, the other topic in 14.4 is tangent plane and linear approximations. So I'm going to put in parentheses, what do you mean by linear approximations? A tangent plane approximation. The good news is you're staring at the formula. Now this is the equation of the formula. Do you remember doing linear approximations in Calculus 1?
Mm-hmm.
This is very similar, except now we're doing what's called, it's still called a linear approximation. We'll just call it a function L of x and y, but we'll use the same formula. So linear approximation will be the same formula here. I just got to solve for z. That's all. So when I solve for z, what would I get? That would be my equation for the linear approximation. What would z?
Plus z naught.
Z naught plus the
Just a bit.
fx value evaluated at the point. Here, I'll squeeze it in there. Times x minus x naught plus fy evaluated at the point. I'll squeeze it in there. X naught, y naught, y minus y. All right, it's the same equation, right? So what I did was add a z naught to the other side. So please remember linear approximations, also called tangent plane approximations, is the same thing as the equation of a tangent plane, except you're just solving for z. And you know how they like to write this? You probably remember in Calc 1 they wrote this as L of x for linear approximation. Well, now it's a function of two variables, so we write it as L of x and y. L of x and y. And again, if it helps, sometimes I don't write all that jargon there. I'll just go fx times x minus x naught plus fy times y minus y. Maybe that looks a little bit prettier. I didn't write the little x naught, y naught thing in there, because you know that you're always going to evaluate the slope at the points. So I'll give you a problem. But good news is, like, I don't have to memorize a whole new formula or equation. It's the same thing. Okay. All right, try this one. For h of x equal to, how about sine of 3x plus cosine of 2x plus e to the 2x plus y. At the point, so this is interesting. They only gave you the x and y. Here's what I was talking about. But for this function, can you find a linear approximation? Find the linear approximation. To h of x. And all this is, if you're curious, this is just there's some, you can think of a three-dimensional surface. You're able to make estimates right off that surface at different points. So can you find the linear approximation to h of x at that point? 0, 0. All right. So I'll write this out. L of x comma y, aka z, equals, I gotta put something there. And when I'll pretty this up, I just want to start there. What did I forget? I didn't want to forget something.
Z naught.
The z naught. That when you do this, that there's a z naught here, z naught added to that, right? I'm gonna put that here. The second thing is you might say, well, this wasn't an f, it was an h. So I can use h, x, h, y, but this is looking good, right? And I just gotta add this to this. That's all. This would be the linear approximation to h of x at 0, 0. But what the heck is what I was talking about. They did not give you that number. Last few problems I gave it to you.
Me too.
And how'd you get that?
Just plug in the 0 for X and Y and see what it
Outstanding. He just took these two numbers, that's X naught, and that's Y naught. He plugged it into the original function of H, the original function to find the corresponding Z naught value, which would be just H of those two values. So when you agree it's a 2, he said sine of 0 is 0, plus cosine of 0 is a 1, plus e to the 0 plus 0 is another 1, and he's getting a 2. But he's getting this number. I must be clear, because you might look back at your notes and go, where did the 2 come from? Because it wasn't given. He just plugged these two numbers throughout the original H of X. This wouldn't give it, you have to figure it out. Cool, so you won't let that bug in, it does. Alright, this is a partial derivative. What's partial respect to X? Oh, and this was a Y, I apologize. That one right there? Right? Let me look. Is it? Oh my gosh. My apology. Keep it an X. I thought they changed it on the. This is the only place where you have the Y. So when we're doing our partial derivatives, we'll just be really careful. At least I know what this is. X minus the 0. This is Y minus the 0. But what's this partial derivative? What's that partial derivative? What's the partial respect to X? I get 3
Cosine 3.
cosine 3x.
Minus 2 sine 2.
Ooh, minus 2 sine 2x. Chain rule. What's your that respect to x?
2
2
e.
Plus 2 e to the 2x plus 1. And then, remember, this doesn't all get jammed there. You will always put a number here, numerical. Numerical slope. That's what it represents, the slope in direction of the positive x-axis of this surface. That's 3 minus 0 plus 2. 5. So all that evaluated at that point. All this. I can just read all over. All this at the point 0, 0. This derivative should be easier. What's this? Partial respect to y? Just deal with that.
Just e to 2x.
Just e to the 2x plus y. Right? Because the derivative of x, e dx, and 2x is just a constant, you gotta, so the e to the 0 plus y, you know, oh, excuse me, you rewrite this and then you multiply this by 1 there. And you gotta plug in a 0, is that just 1? Done, there you go. Okay, I'll let you copy this.
Was it intentionally written as h of x, not like h of x and y?
Oh, it should say h of x and y, and I think there's a typo on that. You just brought up a really good point. That should be a function of x and y, but I copied it from the sheet, and now you're realizing a typo off the paper here. Or my eyes didn't see the y. That's really what happened. I was trying to do one like number 9 on the practice set. If anybody's curious, but it did have a function of x and y.
That was this one.
Yeah. Yeah, this one right here was like number 9 on the practice set. And they had this right here did have a comma y, it was a function of x and y, and that should be there. Man, Matt, thank you again. I appreciate that. Was that okay with this? That's the linear approximation, that's the tangent plane approximation. What do they have you do with this? Sometimes they'll say now use your linear estimation, this would be like an extension. To estimate let's see, when they ask this, I'm going to make up some numbers. These will be numbers really, really close to 0, 0. But use your linear estimation, or approximation. That's a more appropriate word. Use your linear approximation to estimate L of, okay, 0, 0. How about 0.1 and negative 0.1? we don't have to do it, but what would you do? What would you do with these two numbers? Just substitute it into the what? Yep, you don't have to do it now, I just want to make sure you know what to do. That's the idea, now you can use this and you can estimate values that are really close to it. But when they ask this, you'll notice they always give values very close to it because, everyone think of a surface, and you got a tangent plane at this point. Well, what happens to the tangent plane as you get further and further from this point? The tangent plane keeps what? Extending further and further away, right? That's the idea. So when they ask that, it'll be something really close to it. Sort of like you did in Calc 1. They'd be like, use it to estimate and they give you a value right close to where you were getting at. The point that was used. If they used x equal to 2 in Calc 1, okay, estimated about like 1.9. Excellent. Hey, we're gonna do the same thing, but this time it's like right now, we just talked about linear approximations, tangent plane approximations, and you have to be honest, you sit there and you're kind of like, where the heck is that helpful? What is that? Where is that gonna help us? So we're gonna do a problem like that. It has a table. I can pop open the screen here real quick. You can see the table. And I'll pass it out to you. So we're going to do a linear approximation problem. Well, one that has, its application. We're going to do one like number 5. In this sheet. So, these are just some practice problems that I added. I'll pass them out. Can you pass one back? Thank you. We're going to do number 5 together from the sheet. And the only reason I wanted to pop it up here is so you can see the table. Again, I want to save the amount of time that you'd have to sit here in class and copy